Today we continue with our grand tour of light. In the last few classes we talked about reflection, refraction, we talked about mirrors, lenses. Today's class, next class, we're going to move on to two properties. One of them's interference and one of them's diffraction. They're both properties of waves, they're not properties of particles. So in today's class, I want to go through these bullets. I want to talk about interference. What is interference? What is interference of water waves, sound waves, light waves? And then we're going to talk about two very specific cases of interference, two very specific examples of interference. We're going to talk about what's named two-slit interference. And that's a experiment that we can perform, two-slit experiment. And we're going to talk about soap bubble or thin film interference. And that's a natural phenomena that we can observe. Out of today's class, we'll discover the nature of color. What is color? And what is color has only been known for about 200 years. So we'll discover that in today's class. Out of today's class, we'll discover how to measure, how it's possible to measure the wavelength of light. So the wavelength of visible light is from 400 nanometers to 700 nanometers. That's the range of wavelengths of visible light. Now, what sort of scale is that? Well, so let's start with a meter. You know, this is about a meter. 1,000th of a meter is a millimeter, where you can see a millimeter. 1,000th of a millimeter is a micron. That's 10 to the minus 6 of a meter. You can't see that. And wavelengths of light are fractions of a micron. So they're incredibly small, but we're discovering in today's class how you can measure wavelengths of light from 400 to 700 nanometers. Okay, so just to stress again, why is interference of light so important? It's so important because it demonstrated the wave-like properties of light. If we went back hundreds of years to the time of Newton, a very famous physicist, and Huygens, a Dutch, also very famous physicist, at the same time, these guys were arguing. So like normal people, I might argue about who's doing the dishes or whether you drive too fast or too slow. They argued about the nature of light. They argued about whether light was a particle, that was Newton's view, or whether light was a wave, that was Huygens' view. And that was an argument that they undertook and went on for centuries. People arguing, scientists arguing about the nature of light. The problem is that reflection and refraction, the two topics we've been talking about in the context of mirrors and lenses, reflection and refraction can be explained by light being particles or light being waves. So the observation of reflection and refraction doesn't distinguish between light being a particle or a wave. But interference, the effect we'll explore today, and diffraction, the effect we'll explore next week, those phenomena are only a property of waves. They're not a property of particles. And so that's the importance of interference today and diffraction in the next class. Okay. So let's introduce the idea or the phenomena of wave interference. The starting point is to imagine the collisions of waves. They might be water waves, sound waves, light waves. versus the collision of particles, maybe a baseball or a billiard ball or a football. Collisions of waves and collisions of particles are very different. So if you have a collision of particles, which is probably more familiar, then a collision of particles, sort of one particle approaches another particle, then there's kind of the collision, a moment, an instant, a kind of one particle pings off the other particle, and then one particle is receding from the other particle, and that's after the collision. So with particles, there's sort of before the collision, the two particles approaching one another, then there's a moment of collision, and then there's the two particles receding from the collision. It's quite different for waves. You know, when waves collide, there's a period in which the waves kind of converge on one another. They then merge together with one another, and then they reappear and diverge from one another. So it's not like approach, ping, and then recede. It's a much smoother, a much more continuous coalescing of the waves, then merging of the waves, and then decoalescing of the waves. So they approach one another, they converge on one another, they merge with one another, then they diverge from one another. And it's in that process that we see interference, and we're going to see constructive and destructive interference. So I've got two slides here, one to show you constructive interference, and the next one will be destructive interference. And these are two categories of interference that we're used to understand today's class. So over here on the left are two waves, and they're going to collide with one another in the sense that I mean that they're going to merge with one another to make a combined wave. So here are the two separate waves that we're going to add together or merge together. And over here on the right is the resulting wave from the merger of these two separate waves. So this is kind of the superimposed wave. So this is an example of a collision of two waves where there is constructive, what we call constructive interference. So in constructive interference, the key thing is that the crest of wave number one, so here's the crest, combines with the crest of wave number two to make a bigger crest. And so that's how they interfere constructively to make a bigger crest. The trough of wave number one, here's the trough of wave number two, they combine together to make a deeper trough of the superimposed, the resulting wave. And so on and so forth. So this crest here and this crest here combine together to make this bigger crest here. This trough here combine together to make this deeper trough here. That's constructive interference of these two individual waves to make a resulting wave that has a larger amplitude. So destructive interference is the reverse. Again, destructive interference is when we're going to have two waves combining with one another, converging on one another. But in this case, the two waves are going to combine together to make a resulting wave on the right-hand side here that is much smaller. In fact, these two waves here combine together to basically destroy one another and make this region. So what's happening here, this crest on wave number one combines with this trough on wave number two. And the crest and the trough cancel one another out to make this flat region here. Later on, this trough of wave number one combines with this crest of wave number two. The trough and the crest again cancel out one another, and we get this region here. And so on and so forth. This crest combines with this trough to cancel one another out. This trough combines with this crest to cancel one another out. And we get this resulting superposition of the two waves, which is an example of what we call destructive interference. The crest of one is being destroyed by the trough of the other, and vice versa, the trough of one destroyed by the crest of the other. So this is the other sort of category of interference. So you can both, when you have interference, you can build a bigger wave by constructive interference. You can build a smaller wave by destructive interference. Here's a summary of all that to introduce two terms, to introduce a bit of language, which is phase is one of the terms and coherence is the other one of the terms. So let me explain these two terms. Firstly, over here on the right, no, this is the left. Over here on the left is this picture of constructive interference that we discussed. So this is the case where the two waves, crest met crest, trough met trough, we made a superimposed wave that was built out of constructive interference. It had a larger amplitude. And then downstairs here on the bottom left, this was the other case of destructive interference. This is where crest met trough and trough met crest. This was where the waves cancel one another out, and we got this resulting superposition of the waves. This was destructive interference. The phase of a wave, when we say the phase of a wave, what we mean is where we are in the cycle of the wave. So the cycle of the wave is this cycle from crest to node to trough to node to crest and on and on and on. That's the cycle of the wave, and a particular phase is a particular location, position on that cycle. So the crest is a particular phase. The trough is a particular phase. The node is a particular phase. We can denote phases by angles from 0 to 360 degrees that take us from one crest to the next crest. So that's what we mean by phase. In the case of the constructive interference, these two waves are in phase with one another. There's 0 degree phase difference between them. So crest and crest occur at the same time. Trough and trough occur at the same time. So here the phase difference between the two waves is 0 degrees, and that's what characterizes constructive interference. In the case of destructive interference, well, when we have one crest, the other wave is a trough. In this case, there's 180 degrees phase difference between the two waves. So when one's a crest, the other's a trough. When one's a trough, the other's a crest. That's 180 degree phase difference, and that causes the destructive interference of the two waves. And this feature is the key feature in understanding the interference patterns that we're going to explore in today's class. We're going to see destructive interference, we're going to see constructive interference due to the phase differences between two interfering waves, two colliding, coalescing, converging waves. We'll see their phase differences, we'll see the resulting constructive, destructive interference. Okay. Here's just a picture of interference of water waves. So we're looking at the surface of a pond, and I threw two stones into the pond. One landed here, one landed over here on the right. So we've got one on the left and one on the right. That creates ripples in the surface, waves in the surface of the ponds, ripples emerging from where the left-hand stone hit the water and where the right-hand stone hit the water. And we're seeing these circular waves emerging from these two locations. So circular waves emerging from this point where the stone hit, circular waves emerging from this point where the stone hit. Those waves are colliding with one another. Those waves are coalescing with one another or converging on one another or passing through one another And we see that, for example, downstairs here. Look at this region here. It's really interesting. What you see is regions of dark and light. And what you're seeing here is regions of dark and light where you're getting bigger crests or bigger troughs due to the coalescing, due to the constructive interference of the waves. Between the regions of bright and dark, where you're getting larger crests and larger troughs due to constructive interference, are actually regions of destructive interference, where the water's surface is almost smooth. The color is somewhere between the bright and dark. That's where you're getting the destructive interference of crest meeting trough and trough meeting crest. So in this region here is an illustration of interference, is an illustration of destructive constructive interference, is an illustration of waves being in phase with one another, 0 degrees phase difference, out of phase with one another, 180 degrees phase difference. All that's going on in this region of overlapping waves here. Okay, now we could see the constructive, destructive interference patterns of water waves because the wavelength of water waves is in a pond would be centimeters, scales of centimeters or tens of centimeters. And so it's easier for us to see the constructive, destructive interference between converging, coalescing waves when the wavelengths are centimeters or tens of centimeters. But how are we going to see the constructive, destructive interference of light, where the wavelengths, we said, are fractions of a micron, fractions of a part in a million of a meter? What we're going to discover is an ingenious experiment that allows you to see at that scale of a part in a million of a meter and see the destructive, constructive interference of the light waves, and also a natural phenomena, soap bubbles, thin films, that allow you to see the constructive, destructive interference of visible light, which has wavelengths of a fraction of a micron. So we're going to explore these two topics. Okay, so the first topic is two-slit interference, what's called the two-slit experiment. It was developed by a scientist called Thomas Young. He was around 200 years ago, and this experiment was done a little over 200 years ago. He's quoted as being the last man. This is a famous quote about him. He's the last man that knew everything, right? He was absolutely interested in everything. You'll be interested that he was actually a doctor, and he was interested in how we see and how we hear, so light and sound, and that led him to this physics experiment. But he did absolutely everything. It was a time when scientists could do all sorts of things. Now we're so specialized, we know everything about something that's almost nothing. So he was the last person that knew everything, is what they call him. You should look him up on Wiki. It's quite interesting. Anyway, he developed a two-slit experiment that demonstrated two-source interference of not water waves but light waves. So you could see the interference of these light waves that have this tiny, tiny, tiny wavelength. So here's basically a picture of how it works. Over here let's start on the left-hand side. So this is the two-slit experiment that demonstrates two-slit interference over here on the left. Light is coming in from the far left. So these are wavefronts of light. Imagine this is the crests and the troughs of a light wave approaching a obstacle. This vertical line here is an obstacle, opaque obstacle that has two tiny holes cutting it. So there's this upper one, S1, and there's this lower one, S2. So the light strikes this obstacle, but there's like two little pinholes or two little slits cut in it. They're very narrow slits, fractions of a millimeter. So some small fraction of the light passes through the upper slit, it's called S1 here. Some fraction of the light passes through the lower slit, called S2 here. And this creates two sources of light. Actually, what we would call two coherent sources of light. When a crest is coming out of one slit, a crest is coming out of the other slit. When a trough from one slit, it's a trough from the other slit. They're coherent. These light sources are in phase because they're made from one source of light. So it's created with this obstacle, with the two slits, two sources of light, and we're going to collide those two sources of light. We're going to watch them coalesce, converge, interfere with one another. And that's what's going on over here. The way this picture is, it looks crazy, but if you look at this picture in detail, there are light brown wavefronts and there are dark brown wavefronts. So the light brown wavefronts are the wavefronts emerging from the top slit. The dark brown wavefronts are emerging from the bottom slit. So you maybe can see it up here. There's dark brown, light brown, dark brown, light brown. So these are the wavefronts that are emerging from the two different slits. If a crest meets a crest, then you're going to get constructive interference. So where these guys cross, that's going to be constructive interference. If a crest meets a trough, then that's going to be destructive interference. So between the locations of constructive interference, here's one, this red dot here, because this is dark brown line, light brown line, crest from the two slits. Meeting, this is constructive interference. There's another constructive interference over here, this one here. But between those two is a region where crest meets trough. That's going to be destructive interference. And that's what these black dots are indicating. So the red dots are where crest meets crest, trough meets trough, you get constructive interference. The black dots are where destructive interference, where trough meets crest and crest meets trough. And so you see this pattern of red lines and black lines, red dots and black dots, that are indicating the regions of constructive destructive interference. What you see is, and this is the important pattern that emerges from all this, is that along certain directions, the red lines, these are certain directions, these are certain angles away from the two slits, you get constructive interference along those directions. Along directions in between those lines, you get destructive interference. That's the lines made by the black dots. That's where you've got destructive interference. So in those directions. If you were to put a screen here and view the light, we place a nice screen here, what we would see is at the location of these red lines, where they meet the screen, that would be bright regions of bright light, because we're getting constructive interference. So we get constructive interference here, down here, in the center here, below here, and down here. Those are all regions of constructive interference. And then between them, where the black lines meet the screen, that's the regions of destructive interference. And so we would actually see no light. You know, light from both sources is shining over here, but at these locations that line up with the black dots, you actually see no light because of destructive interference. Light from each slit is arriving there, but they're destroying each other in destructive interference. You see this pattern here. This is the pattern you would see on the screen. So this is a diagram, but this is a real photograph of two-slit interference showing the pattern. Showing the pattern of the bright red fringes are the constructive interference. There's one in the center. Then there's neighbors upstairs and downstairs, and then there's further neighbors, 2 steps up, 2 steps down. And then between them is the regions of, the black regions are the regions of destructive interference. We label all this because we're going to work with equations describing it. This central bright spot or fringe or maximum is labeled with an integer. We normally call that integer m. This is the m equals 0, the 0th order maximum. Immediately above it and below it, the next bright regions or spots or fringes are called the first order maxima, m equals 1. And immediately above and below them is the second order bright fringes or spots or whatever, and they're called the m equals 2. They're the second order maxima. And then between them are the minima, and we label those as well. The first minimum as you walk away from the center, so there's going to be one upstairs and one downstairs. That's the m equals 0 minimum. And then the next one upstairs here, and actually the next one downstairs here, those are the m equals 1 minima. So we label all of these things. Gosh. Completely out of control on this now. I actually walked to the end of the class here. I really have walked so far away there. Okay. This shows you a little detail of what's happening for the 0th order bright fringe. That was the one at the center, if you remember, half an hour ago when I was trying to change the slides. This one shows you the 1st order bright fringe. That was the next one immediately above or immediately below. We're seeing the one below here. And then this is the 0th order dark fringe. Remember the bright fringe in the middle has the 0th order dark fringes just above it and just below it. These three pictures depict the light waves emerging from the top slit and the bottom slit heading towards those locations and their interference at those locations. For the center 0th order bright fringe, you see here's the wave from the top slit, here's the wave from the bottom slit. These waves, as they flow from the top and the bottom slit to the screen, you see their crests and their troughs. If you were to count how many crests there are, there's 6 along this bottom wave, there's 6 along this bottom wave. It's exactly the same distance that this top wave and this bottom wave are traveling. They arrive at the slit at this location here in phase, and that's why you get the bright fringe here. If we look at the 1st order bright fringe, what is happening over here? Why do we get another bright fringe? These two waves don't travel the same distance from the two slits to the screen. They're going downstairs here because this is the below the center of the screen. That means that this wave has traveled less distance. This upper wave from the top slit has traveled more distance. But we're still getting a bright fringe. Why is that? It's because if you count the number of waves here, number of crests, there's 6 on this path from the lower slit. There's 7 on this path from the top slit. So this has traveled one extra complete wavelength, which means that they still are in phase with one another. Still crest meets crest, trough meets trough. And so that's the 1st order bright fringe. That's what's happening. The path wasn't the same, but the path was one extra wavelength different. For the destructive interference, above and below the center of the screen where the bright fringe is the 0th order destructive interference. What's happening there? What's happening there is, again, there's a difference in the path to that location on the screen. In this case, because we're looking below the center of the screen, we see that the wave from the bottom slit has traveled less distance. The wave from the top slit has traveled more distance. And what's happening is that the wave from the top slit has actually traveled half a wavelength more than the wave from the bottom slit. You see this, look at this last crest from the bottom slit. Just reaches the crest, just goes over the crest. Well, the last crest from the top slit, we reach the crest, we go over the slit, over the top of the crest. We're not quite there at the screen yet, and so we actually get one more trough in before the screen. So we have the opposite phase. We're out of phase by 180 degrees. We get destructive interference. Okay, show a demonstration. I'm going to show a different demonstration to this one. I'm going to show you how Thomas Young originally did his experiment, how he did the two-slit interference experiment. The way he did it was he covered up, his bedroom window with newspaper, and he made a little hole in that newspaper, and just a stream of light came in through that hole. So that was his source of light. And then he hung a wire, a very thin wire, in that stream of light, so that the light passed either side of that wire. Some light went on the left, some light went on the right. He had made two sources of light with his wire. He basically split the beam of light into two, and then he looked at the interference pattern on his bedroom wall created by the wire creating these two beams of light. And he saw this pattern that we just saw in the overheads of bright fringes and dark fringes, and he interpreted it as light being a wave and the interference of the waves traveling on either side of the wire. So I'm going to try and show you that now. I've got to turn the lights out in a moment, but I'm not going to cover the back door with newspaper and make a little hole in it and get the light that way. We've got a laser pointer now. So this is a laser pointer, and I'm going to turn it on. You can't see yet, but I have turned it on. And I'm going to shine it onto this thin wire here. So vertically here, I've got this very thin wire. And I'm going to try and get the laser beam, if I can do it, to hit the wire such that some fraction of the laser light goes in front of the wire on your side and some fraction goes behind. And so that's creating two sources of light, like two slits of light. That light's going to stream over up to the wall, right above, right up here. You can see it right now. I'm not hitting the wire yet. And we're going to see on the wall the interference pattern. And so that's what I'm going to try and do. Good luck. Okay, so I am hitting the wire now, I think. And I hope you can see there is a really bright central spot on the wall. So that's sort of an overwhelming spot. But look out to the left and the right of that central spot. If you look out to the left and right of that central spot, you see kind of a line of light going horizontal, almost horizontal. But you see it has lots of little spots in it. And between those little spots are little regions of darkness. That is two-slit interference. You are seeing the interference pattern, constructive, destructive interference from the light that's going either side of the wire. And this is exactly what Thomas Young did 200 years ago in his bedroom. And this was really the proof that you see this interference pattern, that light has wave-like properties. And so this is exactly the two-slit experiment. Well, of course, we'll write an equation for the two-slit experiment, and that's what's on this slide. On this slide, I'm picturing that important feature, right, that we discussed on the previous slide, that the light from the two slits in general travels different distances to the screen. One of them's nearer, one of them's further away. And the amount by which the distances are different, I called it delta here. So R1 is the length of the line from the top slits to the screen. R2 is the length of the line from the bottom slit to the screen. They are different depending on where you are on the screen. That difference, I called it delta. And that difference, by a little bit of trigonometry, depends on how far apart the slits are. You would imagine it would depend on how far apart the slits are. If you made them at the same location, there would be no difference. For example, if you move them further apart, there's got to be more difference in the path. So it's going to depend on D, this separation of the two slits, and it's also going to depend on this angle that they head towards the screen. If they headed towards the center of the screen, 0 degrees, then there'd be no difference. But if they head up towards the top of the screen or down towards the bottom of the screen, there's going to be a big difference. So the extra difference in path is, by a little bit of geometry, you can write it as d sine theta. So d is the slit separation. More slit separation, more difference in path. And theta is the angle that the rays take to the path, the angle from the center of the slits to the location on the screen. And so the bigger theta, right, the bigger the extra distance of one ray compared to the other ray. If theta was 0, there is no difference. So you can write this extra distance as d sine theta. We often do that. We also often write it this way. We still have the d, but we replace the sine theta, the angle, with two things that are easy to measure in the experiment. They are the distance to the screen, that's the L here, and they are the location on the screen, that's the Y here. Now, strictly, this is an approximation. It's called the small angle approximation, but it applies if this angle to the screen is small. And generally, this angle to the screen is small. In my demonstration of the two-slit experiment, right, the laser beam hit the wall up here, and it was just a fraction of a degree to the left and right that you saw the pattern of interference. So the angle is normally small. This is normally a good approximation. These are just two different ways of writing this same quantity, the extra distance, one in terms of the angle, which tends to be less handy. We normally are measuring the location of the slits on the screen. So the second one is in terms of the location of the slits on the screen. Okay. So these are the equations that tell us where the bright fringes are, where the dark fringes are. Where the bright fringes are is where that extra distance that one ray travels compared to the other is a whole number of wavelengths. And where the dark fringes are is where that extra distance that one ray travels compared to the other ray is a half integral number of wavelengths. I mean, half a wavelength, 3 halves a wavelength, 5 halves a wavelength. And so that's what this quantity is here, m lambda. This quantity is here, m plus a half lambda. This is a whole number of wavelengths. M goes 0 or 1 or 2 or 3. This is a half integral number of wavelengths. This quantity goes 1 half, 3 halves, 5 halves, 7 halves, and so forth. And so the left-hand sides of these equations are the half or the half integral or whole integral numbers of wavelengths that give you constructive or destructive interference, and the left-hand side, so this extra distance, either written as d sine theta or written as dy over L. And so these are the two equations that we use to describe the locations of the bright and dark fringes on the screen, and to quantitatively understand the pattern of destructive and constructive interference. So let me just show you an example of using them. And it's how we could have used our little setup, our little demonstration here. A two-slit experiment with a 2.1 millimeter slit separation and a 1.75 meters screen distance has 0.55 millimeters between the first and second order bright fringes. We've got to find the wavelength. Find the wavelength of light that corresponds to this. You know, when we did the demonstration, I had a green laser pointer. Well, what's the wavelength of the green laser pointer? Well, I shone it on the wire that created two sources of light that were separated by the thickness, the diameter of the wire. It shone onto a screen up here that was 5 meters away, or whatever it is. And so I could calculate the wavelength of the laser light from the pointer, knowing the thickness of the wire, the slit separation, knowing the distance to the screen on the wall here, and measuring that little distance that we saw between adjacent bright fringes. And so this example is a quantitative example of exactly what we just did in the demonstration, what Thomas Young, exactly what he did. So he's going to calculate the wavelength of light. And think about it when he did it 200 years ago. Firstly, nobody knew that light was a wave. Secondly, certainly nobody knew what wavelengths visible light had. So it was an amazing step. And he wasn't even a physicist. He was a doctor that figured this out and just was interested in light and sound and did this experiment. Okay. Why am I going over here? I'm going over here because I was going to do it on the document camera, which I haven't used for a while, so I don't know how to switch on anymore, apparently. Here we are. I got to look up the numbers, of course. So we were told several numbers in the problem. We were told that the slit separation, what we call D traditionally, is 2.1 millimeters. We were told that the slit to screen distance was 1.75 meters. We were told that the separation between the first and the second order bright spots was 0.5 millimeter. It was actually 0.55 millimeters. So these are the three things that we were told. And we could imagine when we did the experiment that we actually measured these things if we liked. The key equation that we're going to use is that if we're thinking about constructive interference, that occurs when you've got a path difference. There's a whole number of wavelengths. There's m lambda. And that's going to be equal to yd over L. That's the geometrical equation for the extra distance that's traveled. Now, in our particular case, we've got the first order maximum. That's where that extra distance is one wavelength. And in that case, m is 1. So over here on the left-hand side of the equation, I just got lambda. And that's going to be equal to y1. I'm going to call that the location on the screen of that first order maximum. y1 times d divided by L. So that's one equation. And then the second order maximum, that's where the extra distance is 2 wavelengths. So imagine those spots on the wall. There was the one next to the really bright spot. That's the first order. We're measuring the location of it. There's the next one. That's the second order. We're measuring the location of it. It corresponds to 2 extra wavelengths. And so that extra distance is 2 lambda. And by a little bit of geometry, we said that this is equal to its location, y2 times d divided by L. So we've got these two equations for the two locations. I'll call them 1 and 2. If I take the difference, of these two equations, remember I didn't tell you y1, I didn't tell you y2 in this problem. We measured the difference between them, and that's typically what you would do. That's what we would do if we measured the difference between them on the wall. So if I take the difference of these two equations, on the left-hand side I'm going to get 2 lambda minus a lambda, so I'm just going to get a lambda again, the wavelength. On the right-hand side I'm going to get y2 minus y1, and then multiplied by these common factors of d over L. And then if you look at that equation now, over on the left-hand side, we got the wavelength. That's what we were trying to figure out. Over on the right-hand side, we got the slit separation. We know that. We got the screen distance. We know that. And we got this measured difference between the second and first order bright fringes. Every number here over on the right, we know. And so I can just plug them all in. And so I'll do that. I'll try. 2.1, no, what am I doing? I've already done it wrong. It was 0.55 millimeters. So that's 10 to the minus 3 meters. Times d, that was 2.1 millimeters. That's 10 to the minus 3 meters. Divided by that screen distance, that's 1.75 meters. And if I calculate that, I've already done it, of course, 662 nanometers. 0.66 microns, 662 nanometers. 662 nanometers is a wavelength of visible light. If you remember, 400 nanometers, that's the shortest wavelength of visible light. That's sort of kind of violet. 700 nanometers is the longest wavelength of light that's visible. That's red. And so this is close to that. This is a sort of maybe a reddy orange color. And so we figured out the wavelength of light. By doing this two-slit experiment, when we shone that green, for example, in this case, the green light onto the wire, we made two sources separated by the thickness of the wire. We saw the interference pattern on the screen meters away. You're able to see in this experiment the wavelength of light. This thing that is a fraction of a micron, we can actually see it through this interference pattern on the wall. And so that was a huge achievement. Let me say that nobody believed Thomas Young, of course. Newton was such a, oh yeah, thank you. Newton was such a massive figure in physics, and Newton had said that light was particles, that nobody believed Thomas Young to begin with. And actually, he quit his physics experiments. He went back to being a doctor and doing other things. But in the end, he was proved right. Light was exhibiting wave-like properties. He had explained the origin of color. Color simply reflects the wavelengths of the light. And so it was a really historic experiment and a historic development. What am I doing? Yeah. Where am I going? PC. Let's have a quiz question on all that. Where's my quiz? So this is a quiz question about the two-slit experiment. Imagine doing the two-slit experiment, and then imagine that you change the wavelength. You increase the wavelength. So if you increase the wavelength, you would go from the short wavelength, blue end of the spectrum, towards the red wavelength, the long end of the spectrum. So if you do that, do the bright fringes get closer together on the screen if we were to do that, or do they get further apart? That's the question. So in this question, we're changing the wavelength. We're making the wavelength longer. We're going from blue light, short wavelength, to red light, long wavelength. If we make the wavelength longer, then to create an extra path, a path difference between the two slits, if the wavelength is longer, we need a longer extra path. To make a longer extra path from the two slits, we've got to be at a larger angle on the screen. We've got to be at a greater position on the screen. So if you make the wavelength longer, you're going to need a greater path difference between the light coming from the two slits, which means that you need a greater angle on the screen to make a particular bright fringe, a particular dark fringe, which means that you need a greater displacement on the screen from the center of the screen to make that bright fringe or that dark fringe. So increasing the wavelength will increase the separation between the fringes, increase the angle of the fringes, increase the location of the fringes. It increases everything because you're increasing the size of a wavelength. I've already mentioned this, but it is a really key point. Until 200 years ago, nobody knew what color was. I mean, you know what color is different colors. There is red, there is blue, there is green, there is yellow, there is orange, and so on and so forth. But what is red, blue, green, orange? What red, blue, green, orange is different wavelengths of electromagnetic waves. And Thomas Young was the person that made that discovery, the correspondence between color and wavelength. Really having major problems with this today. Okay, let's talk about soap bubbles. So soap bubbles, turns out, are natural phenomena that also exhibit interference of light, constructive, destructive interference of light. And so in irony, it needn't have waited for Thomas Young two-slit interference, which was an experimental setup that allowed him to look at interference, light interference. We could have just looked at a soap bubble. Isaac Newton could have just looked at a soap bubble. And if he'd just been smart enough, he would have figured out that that's proof that light is a wave, not a particle. So let's see how this works. If I can control this thing for more than a second. So this slide is a diagram of how soap bubble interference works, how in a soap bubble you see rainbows of colors of light. So remember, when you're, I don't know, you're a teenager, you're blowing soap bubbles, And these amazing soap bubbles, you look in them and they've got all sorts of colors to them. All these amazing colors, that reds and violets and greens and blue, and it's all changing all the time as they float around. It's just an amazing thing to look at, I still think. How do all these colors come about? How does this colored pattern come about? Well, it comes about because of light's a wave, comes about because of interference of light, comes about because of constructive destructive interference of light. This is how it works in this picture over here on the left hand side. When we see light from the soap bubble, what are we really seeing? Well, some light from, say, the sun is striking the soap bubble, and it's reflected off the soap bubble and entering your eyes. So when you see this colored pattern in the soap bubble, if you're outside, what you're seeing is the reflection of sunlight off the soap bubble, and you're seeing that light. But the important thing is that that light is reflected off both the outer surface of the soap bubble and the inner surface of the soap bubble. So the soap bubble, as you know, it's a very, very thin, spherical, hollow bubble of soapy water. And it's extremely thin. You know, it's microns thin, the soap bubble. And light is actually reflected off, sunlight says, reflected off both the inner and outer surfaces of the soap bubble. So when you look at a soap bubble, you're actually seeing reflected sunlight from the inner surface and the outer surface of the soap bubble. That's what I'm drawing here. So this is a little cross-section of the soap bubble. So just imagine a little piece of the soap bubble in here, and we're looking at a side view of it. This is the outer surface of the soap bubble. This is the inner surface of the soap bubble. These two horizontal lines, these two surfaces here. So here's the sunlight striking the soap bubble, and here's some of it reflected from the top surface, but some of it passes through the soapy water and is reflected off the bottom surface. And what we're seeing is the interference of the light that's reflected off the top surface, I labeled it 1, and the light that's reflected off the bottom surface, I labeled it 2. It's like two-slit experiment all over again. It's like Thomas Young's two-slit interference all over again. Now my sources, two sources of light are not two separate slits or either side of a wire, but rather they are the bottom and the top surfaces of the soap bubble. Those are separated by some very small difference, like the left and right hand sides of the wire, or the two slits in Thomas Young's experiment. And so we got these two sources separated by small distances, and they're interfering, and we're going to get constructive and destructive interference of these sources of light. And if they interfere constructively, if a particular color of light interferes constructively, you're going to see that color as being bright. If a particular color interferes destructively, you won't see that color. And so on the surface of the soap bubble, you see, like here, this is where violet is interfering constructively. And so you're seeing a lot of violet there. And you're not seeing the other colors because they're interfering destructively. Downstairs here, this is green. So here you're seeing green interfering constructively, and the other colors are destructively interfering. And then somewhere over here, here's red. Red interfering constructively, and other colors destructively. So different regions of the soap bubble have different thicknesses. It's not perfectly spherical and perfectly uniform, and so you get different regions of the soap bubble reflecting strongly different colors, violet, red, green, in different locations. That's exactly what you're seeing here, and it's just working like this. Now, as we go on to look at the equations describing it, I want to introduce the key features. If you're going to get constructive interference of these two rays, 1 and 2, this extra distance, you would say that this extra distance must correspond to a whole number of wavelengths. And if you're going to get destructive interference, then this extra distance must be a half integral number of wavelengths. So that's I think that's what we would expect. That's what everybody would expect. There is one bit of a subtlety there. Remember that light, when it enters into a medium, here we've entered into the water, or it enters into the grass, its wavelength changes. Its wavelength changes by this factor, the refractive index of the medium, the water or the glass or the whatever. And so this extra distance here has to be, we would say that it has to be a whole number of wavelengths for constructive interference, but it's wavelengths in the water. So the wavelength in air divided by n is the wavelength in the water. And if this extra distance, we would think, is a half integral number of wavelengths, so half a wavelength, or 3/2 a wavelength, 5/2 a wavelength, it must be half integral numbers of this wavelength in water, lambda over n. So we could write down a little equation that says if this extra distance, which is twice the thickness of the soap bubble, because you've got to go down then back up again, if that's equal to whole numbers of this, that's going to be constructive interference, bright color. If it's half integral numbers of this wavelength here, that's going to be destructive interference, and you won't see that color. So that would be my prediction. I'm sure it'd be your prediction, because we're all experts on interference of two sources of light now. But actually, it's completely wrong. It's completely wrong. It's the wrong way round. They thought they understood two-source interference, but when you predicted the pattern that you would see for soap bubble interference, it was the wrong way round. Where you were expecting constructive interference, you got destructive interference. Where you were expecting destructive interference, you got constructive interference. It was exactly the wrong way round. What scientists realized was that there's one subtlety here, and I wrote it down over here. When a light ray is reflected off a higher refractive index medium, there's a 180-degree phase change of the light ray. So what was a crest becomes a trough. What was a trough becomes a crest. When light is reflected off a lower refractive index medium, that's what's happening at the bottom here, because air's lower refractive index, then there is no change. A crest, when reflected, is still a crest. A trough reflected is still a trough. Nobody had expected that, but that's the explanation of why the pattern is reversed from what you would naively expect based on the extra path being a whole number of wavelengths. What's happening here is that on this upper reflection, there's a 180 degrees phase change, which makes a crest into a trough and a trough into a crest. There's no 180 degrees phase change at the bottom reflection, and so there a crest remains a crest and a trough remains a trough. Because of the 180 degree phase change, this additional 180 degrees phase change, it's actually half integral numbers of wavelengths that create constructive interference, and whole integral numbers of wavelengths through this extra distance create destructive interference, because there's also a half a wavelength change on this reflection. So that whole thing was a famous scientific story. It was it was just what is going on here moment in science, and then this is how they solved it. This is absolutely how they solved it. Give me 5 minutes. I'll try and change the slide. Of course, there's going to be equations. Of course, there's going to be equations for where you get bright colors, constructive interference, where you get dark colors, destructive interference. So what we're going to still call bright fringes and dark fringes. We just went through a lengthy argument about what's going to create a bright fringe and what's going to create a dark fringe. What's creating a bright fringe is that the extra path here is a half integral number of wavelengths of the light in the water. So here's the half integral, m plus a half, so this is a half, 3 halves, 5 halves, 7 halves, etc. Here's the wavelength of light in the water, lambda with the subscript n to remind us this is in the water, the wavelength in the water. And so this is going to be a formula for the bright fringes. And it incorporates this phase change upstairs here. This is the equation for the dark fringe. You get dark fringes when you get a whole number of wavelengths. So m is the counter for the whole number of wavelengths. It's going, 1, 2, 3, 4. Lambda subscript n is the wavelength, but it's importantly, it's the wavelength in that water, in that material that the light is traveling the extra distance through. So it's a reminder of that. We can write these two equations as half integral or integral number of wavelengths in the material, or write it as half integral number of wavelengths in air, and divide that by the refractive index. So lambda subscript n is lambda over the refractive index. Lambda subscript n is lambda over the refractive index. And that has to be this extra distance, which is twice the thickness of the soap bubble. And so these are the two equations. They parallel kind of the equations for the two slit interference pattern that tell you when you get brightly reflected light and where you don't get brightly reflected light, where you get bright and dark fringes. Crap. Oh yeah, let's take a look at a demonstration of this. I will try a demonstration, and I've also got a video of it to show you. Okay, so I've got I'm going to put this on the camera. Oh, wrong camera. I want to put it on the other one. Camera bench. But it's pointing at the wrong thing. And I have no idea where I am on this. Okay, forget it. I've got a cookie baking sheet worth of soapy water. There's nothing you're going to see on the screen because I've got the wrong thing on the screen. But I can get a soap bubble here. So I don't know if everybody can see it. I got a soap bubble here. And I'm going to shake it around in this light. I don't know, I lost it now, whether anybody saw a... Now I've got too many soap bubbles in the soapy water itself, so I can't create a soap bubble. I got one, captured one. Does anybody see anything, or is it just like, oh, somebody did? That's good. I can see it. I can see all these colors, and now it's going to wait. Let me show you a video. Piece of crap demonstration that was. Where am I going now? Okay, so as a backup plan, I made a video of this. So in this video, which I've only got on one screen, so let me put it on both. No, but that's the wrong thing. I want this. I've got the cookie tray filled with the soapy water. I've got that ring that was made from a coat hanger. No expense spared on this one. I've got a soap bubble on here, and I'm going to start wiggling it around as I was trying to do in the demonstration. And you see these bands of color. These bands of colors of greens and pinks and blues and violets and reds. That's where you're getting constructive interference. In this case, it's constructive interference of the light from that lamp. And so you're seeing these patterns when the thickness of the soap bubble exactly matches that extra distance to get constructive interference. I want to do, in the last few minutes, you'll be pleased to know, a quick question involving the soap bubble interference. So in this example, we're told we've got a soap bubble. Its thickness is 120 nanometers. I said soap bubbles are very, very thin. Fractions of a micron. So this is a fraction of a micron. And we've got to calculate, given its soapy water, that has a refractive index of water, 1.33, given its thickness, 120 nanometers, we've got to calculate the wavelength of the most strongly reflected visible light. What color are we going to see in this particular soap bubble? We've just seen a video of a soap bubble. We've seen different colors in it. What thickness of soap bubble will we see? So let's see what color is brightly reflected from this particular soap bubble. Well, it's going to take me the rest of the class to get to the solution, but here it is. Here are the two things I know: the refractive index of the medium, the thickness of the soap bubble. Here's the equation that describes this situation of constructive interference. It's that extra distance, 2t, is a half integral number of wavelengths in the soapy liquid. So this is the equation that I introduced. I've rearranged it, though, for the wavelength. I've rearranged it for the wavelength in terms of the thickness of the soap bubble and the refractive index of the material. So I just rearranged it. So we want to know what color is reflected strongly. Well, at this point, I don't know what value of m to pick. Is it going to be half an extra wavelength distance? Is it going to be 3 halves? Is it going to be 5 halves? Is it going to be 7 halves? I don't know which one of those. We weren't told it. And so all I can do is trial and error. I'm going to start with a half as the extra distance, the half wavelength, see what color of light I get for that. And then I'll go on. I'll do 3 halves. If I'm unlucky, I'll do 5 halves, 7 halves. I'll go on and on to find the wavelength of visible light that gets strongly reflected. So I tried m equals 0. So if I plug in m equals 0 into this equation, in the denominator here, m plus a half becomes just a half. And I can plug in the refractive index. I can plug in the thickness of the soap bubble, n and t. I plug them in here. I got 640 nanometers. That's red light. So it's red light that's strongly reflected in this soap bubble. I was wondering if maybe another color of visible light would be strongly reflected in the soap bubble. So I went on to try m equals 1. I plugged in m equals 1. So in the denominator here, we've now got 1 plus 1 half, which is 3 halves. And then I've just got to, again, take 2 times the refractive index times the thickness of the soap bubble and divide it by this number now, 3 halves. That's going to be 3 times smaller. 3 times smaller than 640 nanometer red light is 230 nanometer non-visible light. This is shorter wavelength than blue light. This is wavelengths that we can't see it. Bees can see it, but we can't see it. This is ultraviolet light. And so there's just